Okay, so hi everybody. Uh, in this video, I'm going to talk a bit about diffraction, which is the other major aspect of wave optics I'd like you to understand. Now, diffraction is a pretty fundamental aspect about how light or any other wave phenomena works, and it places fundamental limits on things like how well you can resolve distant objects or see things in a microscope. So it is a worthwhile thing to understand. And it's another thing that fundamentally depends on the fact that light is an electromagnetic wave. And it's something that is not captured by ray optics. So what diffraction is fundamentally the way light will naturally tend to spread when it passes through an aperture or a hole. If you consider straightforward ray optics, the direction light travels only changes when it hits an interface. So if you have a hole in an object, the light rays that hit that object can either bounce off or be absorbed, but the light that goes through the hole just keeps going straight. And this is more or less sensible when you think about it in most of our experiences. This is a picture from your textbook. You imagine shadows. Shadows can have fairly crisp edges. They're not always perfect, but they're fairly close. So that looks like this picture. You have light going in one direction here, but it's blocked in other locations. Now, for big objects like doorways, etc., this is a decent approximation. But as you consider smaller and smaller apertures, it starts to break down. And even with large apertures like doorways or windows, it's not quite right. In fact, some amount of light passing through any aperture is deflected. It goes out the corners. It doesn't go in the same direction the instant light was, its direction has changed. And this scattering of the light becomes more and more important as the aperture gets smaller, but it's always there. And it isn't like a specific phenomena that depends on whether this aperture is a mirror or something that perfectly absorbs light. It doesn't matter what the edges of the aperture are like. Those both can affect the process somewhat. The fact that light wants to spread out is more fundamental than that. It is something that emerges because this is a propagating electromagnetic disturbance. Now, the book and a lot of other places try to explain this in terms of things like Huygens rule, etc., for how you can think of every point along the wave as a source of electromagnetic waves itself. I kind of find those a little less than compelling because it's like, wait, why does that work? So I'm going to try and give you a little bit of a physically motivated picture to understand why this sort of thing happens. So let's zoom in again. If we look at a region of an electromagnetic wave, then we have a wave moving from left to right, then the thing to note is that at every point in space, there's oscillating electric and magnetic fields. The electric field in this wave goes down, then up, then down again. The magnetic field goes in and out and in again. The thing is, this entire disturbance propagates very cleanly in this direction only if this wave actually extends a decent distance in all directions perpendicular to the direction of the wave's motion. So if the wave is moving from left to right, these oscillations of the electric field have to be the same everywhere up and down and in and out of the page. Same with the magnetic fields. So if at this particular point where the wave is up, if I go, or sorry, where the electric field points up, If I go further up, the electric field points more up. If I go down, the electric field stays pointing up. If I go out of the page, I will still have electric fields pointing up here. By contrast, if I'm over here, the electric field points down. It keeps pointing down if I move up, down, in, or out. Turns out this is the only way to get something that clearly moves in one direction. This does not work if the electric or magnetic fields change as you go up, down, in, or out of the page. To see why that is, let's consider a fairly simple case, I hope, where we imagine an electromagnetic wave passing through an aperture and then coming out over here. Now, and let's just consider what's happening at this point. So we have an electromagnetic wave that's propagating this way. And let's focus on what starts to happen at this point just outside the aperture, okay? What we have here is a place where the magnetic field went from going into the page and is now beginning to get out of the page. So it goes from being into the page to out of the page. So there's an increasing magnetic flux through the loop I'm showing here. Okay, what does that do? Well, remember, an increase in magnetic flux by Faraday's law starts creating circulating electric fields. So this is going to start to create an electric field that points this way up here and this way down here. This is the start of a new electromagnetic wave, not one where it's moving in the direction from left to right, but these are waves that are going to be moving up or down. This is going to start generating light that goes in all directions. And since electromagnetic waves are self-supporting, once you start this, you can't stop it. The light intensity can fall off as it moves away, but this is going to generally cause light to spread. And if you have a very narrow aperture, it basically will spread in all directions. It'll go up, down, at any diagonal with equal intensity. Now, it can't go back through the hole very well, but this is kind of the extreme case. If you just consider what the things like Faraday's law force to happen. Now, if you have a slightly wider aperture, something where there are maybe enough, something like this, now this side, and again, we're going to consider two places here. Both of these are producing increasing magnetic field because this stuff already came through. The magnetic field was down into the page. Now it's coming out of the page, so it's rising. This is starting to create the same process. It's creating something where the electric field wants to point this way up here and this way down here. But now there's another little region of space that contains the same thing, the part from this part of the wave. It's also going from having an electric field pointing down, a magnetic field pointing down to a magnetic field pointing up. You look at a little circle around that. It also has this property. This is going to start to create an electric field pointing this way up here and this way down here. Now, on the edges, we have the same situation we had before. This is going to start to create an electromagnetic wave that tries to propagate up. This starts to create an electromagnetic wave that tries to propagate down. But at this location, in the middle of the wave, those two electric fields generated by these two magnetic fields cancel out because one's going to the left, one's going to the right. That's the normal thing to keep this wave. That cancellation is what keeps this disturbance from deflecting as a whole. This kind of interaction between different regions in the wave which is a form of interference, keeps the wave propagating in one direction in the middle of the wave, but it still begins to deflect near edges. And this will always happen, but it doesn't happen as efficiently because now parts of the electric field that are being generated are canceling itself out. And just to say, this is specifically presented here for electromagnetic waves, but this is the same sort of thing that happens with any wave. If you imagine a sound wave, which is a pressure disturbance, as you come into this region, the pressure might go up or down. That's necessarily going to push on the air right here and cause it to move, creating a new wave. It also tries to create a wave moving in the opposite direction, but similar waves created here cancel it out. So this happens generically, and it means that the larger you make the hole, the less this is relevant. So this means whenever you see diagrams of waves like these, what you will see is that if you have a nice normal wave coming in, then you make a small aperture, you get lots of spreading. You can actually get to almost spreading spherically away from the aperture if you make it small enough. If you make the aperture bigger, then the wave that went through the middle doesn't work like that. So most of the wave happily just keeps propagating forward. But it does get spread a little bit. The wave starts to get a bit wider than this hole. So this always happens, but the amount by which it happens varies. And the thing is, when you do the math of this stuff, the same basic equations that we used previously with interference come into play again, because this cancellation of these electric fields is a form of interference. It's again just the fact that the wave has a direction and a magnitude associated with it, so it can add together or cancel. So it turns out the math behind diffraction is very similar to the math behind interference, and that's why they're often talked about together. Now, it turns out the math behind this is extremely annoying because basically what you have to do is take a bunch of slits and paste them very close together over some range d. But despite that, it turns out that the basic results you get are very similar. That is, whether you get destructive interference or constructive interference basically is determined by the ratio of the wavelength of the light to the size of your single aperture. Now, the math involved in doing this is a little tricky. It involves calculus. We're not going to get into those details here. But at least we can just say that the final expressions we get are close to, but not quite what you'd get from a pair of slits. If you have an aperture of size d, the locations of bright interference occur where d sine theta is an integer times the wavelength. And in these cases, it turns out that it's not where m is any integer, it's where m is 0, 2, 4, etc. Basically what's happening here is it's no longer just the edges that matter. The two edges have to be in phase. It's that some average value of the light coming from each part of this slit has to be more in phase than not. And the math in that turns out to mean that bright peaks tend to occur where m is 0, m is plus or minus 2, m is plus or minus 4. Similarly, you get destructive interference where d sine theta is an integer times lambda for the odd values of m. So again, you get a bright spot, a dark spot, a bright spot, a dark spot, no matter how the light was coming in. So this turns out to have important implications for things like resolution of optical instruments. To understand what I'm talking about, let's go back to our original pictures of how we make images using ray optics. Before, we were pointing out that whenever you want to make an image with optics, you need to have something that registers light, a detector, be it the retina in your eye or some like CCD, and then you need some optical element to actually, control where the light falls on the detector. And one of the simple ways we talked about was just to put an aperture, just to put a hole in an opaque sheet of cardboard in front of the detector. Then light from from one source only hits the upper part of the detector. Light from another source only hits the bottom part of the detector. The problem is, if we make that hole small, the light not only hits that part of the detector that this ray follows, it also spreads out. It hits multiple spots on the detector. And this blue source doesn't just produce light that hits here, it produces light that hits all over the surface. And things you might think would help with the resolution, like making this aperture smaller, can actually make it worse because the light spreads out. This means that anytime we have an aperture in our optical instruments, there's a limit to our ability to measure or to distinguish objects. So in this case, we just have two light sources. If those light sources are far apart, like they are here, you can still tell them apart because most of the light from the red source ends up down here, most of the light from the blue source ends up here. But if they're closer together, these two beams begin to overlap, and that causes problems. So, and this is what you actually see. If you ever look through any optical instrument, you will never get a perfectly clear image. It will always be slightly fuzzy due to the diffractive spreading of light. Now, which means if you have two sources of light, there's a limit to how close those sources can be before they basically merge together. And that's a pretty fundamental parameter. It means what's the smallest separation you can see of some physical objects. And this isn't something like you can change all that efficiently. Now, just to be explicit about this, we're no longer talking about slits here. We're talking about an actual hole in the wall. This is an example diagram here. When we talk about a hole, the geometry changes a little bit, so the rule changes a little bit. It's no longer d sine theta equals 1/2 or 1 or something for where there's a bright fringe or a dark fringe. The number turns out to be 1.22. That has to do with the wonderful world of Bessel functions. You don't want to know about Bessel functions. They're annoying. Anyway, but what it means is that when you have an aperture, the light spreads out. And the amount by which the light spreads depends, again, on the wavelength of the light and the diameter of the aperture. So what's really relevant is, where is the first place relative to the incident light that the signal would fall to close to 0? Remember, for a slit, this is where d sine theta would be 1/2 lambda. But for a circular hole, for reasons, it happens when d sine theta is 1.22 lambda, or where sine theta is 1.22 lambda over d. This is a critical angle. If you have an object that is displaced in angular coordinates from this first object by a bigger amount at that angle, then you can usually tell them apart. Because while the light is spread out, it's not spread out as much as the objects are separated. So, for example, the light from this object produces a big, broad, fuzzy peak centered on this location. This light produces a big, broad, fuzzy peak that's centered on this location. Now, they're blurred together partially, but you can still see there are two peaks. Now, this is part of the issue with how do you represent this, just to be clear on this. In fact, what you'd see is what we saw previously, a big, bright, fuzzy ball, and in the case where sine theta is 1.22 times lambda over d, you see this, where they're partially blurred together, but you can still see there's two objects. If you have less than this, they basically merged. Now, people who do image processing can distinguish that there are two objects here, not one. You could see that it's elongated, for example. But for a practical point of view, this is kind of where your resolution starts being hard to deal with. If you want to see fine scale structure, you want this to be what's happening, not this. And just one last thing to clarify these things. What we're showing, instead of showing this as bright splotches, this is showing a plot of how intense the signal is as a function of angle. And so the bright spot is in the center, it falls down to 0, it then gets bright again and then faint again, but those other peaks are usually much less for a spherical hole, for a circular hole. And that's what they're showing here. What they really should have done is shown little spots with these things above it, but what are you gonna do? So what this means is this angle, where sine theta is 1.22 lambda over d, is a fundamental limit on the resolution of an optical system that has a hole in it. If you restrict the light to come from a region of only diameter d, you are not going to be able to distinguish sources where the angle between those sources at the hole is less than that. Now, you might think, well, I don't use a hole, I use a lens or a mirror. It still happens because only light from within that lens or bouncing off that mirror can get to the detector. There is still effectively an aperture. Only light within this region can reach the detector and be focused properly. So that same rule applies to telescopes and microscopes with a lens. The advantage of putting in a lens is now your aperture can be bigger. You can still focus all the light with a bigger aperture. The diameter of the lens or the mirror is now what sets your resolution. And that's what drives a lot of optical designs, especially ones designed for high resolution. Now, as you know, I'm an astronomer, so the case where this is most dramatic is with telescopes. Because with telescopes, we're always trying to see, like, pairs of stars or stars around, or planets around stars, etc. So this sort of resolution is key. And a lot of basic optical design revolves around the fact that if we want to make our resolution good, we need to make the diameter big. So, just a couple of concept questions to test that out. Here's a couple of pictures of telescopes that exist in the real world. This is the world's largest refracting telescope. It's got a lens at this end and another lens down here. It is in Yerkes Observatory in Wisconsin. It was built in 1897. You can see some people here for scale. And it's what's called a 40-inch refractor because the tube is about 40 inches across. This here is the Euler telescope. It's a different design that's more modern. And it has, instead of a lens, it has a mirror in the back. And so that light gets bounced off the mirror and goes out the side in various ways. They're shown here roughly to scale. There's a person here and a person here, so you can see they're roughly to the same scale. Obviously, this one is much longer than this one. So a question I would naturally ask is, which of these instruments has the better resolution? Is it Yerkes, Euler, or are they both about the same? And I ask you to think about that. The answer is they're both basically the same. The thing that matters for resolution is the diameter of the telescope. The fact this has a much longer tube is irrelevant to that. This has a longer tube because it has a lens. And turns out there's a limit to how well you can focus light with a lens of materials that like existed in 1897. Whereas mirrors, you can fold light a lot better. So that's one aspect of it. What matters is the cross section, not how long your telescope is. Now, another fun thing to think about is radio antennas. We have radio telescopes, and again, these are just things I'm familiar with. This is a fairly reasonable sized one. This is what is known as the Karma array. It's a bunch of telescopes that are fairly big. You can see there's a gangplank here that people could walk on. This dish and all the other dishes are about 10 meters across. So they're fairly big. And they operate at wavelengths around 1 millimeter. So a question would be, which has better resolution? The Karma array, which has 10 meters telescopes across observing at 1 millimeter, or human eyes, which are only 2.5 millimeters across and observe at around 500 nanometers. What do you think the answer is? Turns out they are actually both the same. Lambda over d is similar for both of these systems. So the critical angle for resolution is actually very similar. Do the math yourself to check this. To achieve high resolution at long radio wavelengths is hard. It is it requires much larger telescopes than can be possible in the visible. So this is one reason to think about not only the size of your optical element, but also the wavelength you're looking at. If you have the choice, going to shorter wavelengths is often helpful. Now, I know a lot of people here are biologists, so they don't necessarily care about telescopes, but they care about microscopes. Microscopes, this limit creeps in slightly differently. Because whereas with a telescope, it's like, I can't get any closer to stars or other objects far away. With a microscope, the thing you want to study is right there. So the key thing is when you're looking through a microscope, you want to see a small object, be it a cell or protein or a viral particle, anything like that. But the angle that matters depends on the ratio of that distance, that separation to that distance. I mean, again, it's given roughly by tan theta equals x over d. So if we want to see a small x, we can just make theta bigger by moving the objects closer to the lens. That's what you do. But this limitation still creeps in. One, from a practical point of view, is that remember, to actually see things, we need to magnify them. And magnification only works efficiently if you're a certain distance from the lens, its focal length. So that's a practical limitation. There are also fundamental other limitations. The thing is, as we try to focus the light, even from something fairly close, there's a limit to how well we can do this. The ray optics picture, where all the light gets focused to a single point, that's again unphysical because light can't do that. If this location, we get exactly that same situation we talked about before. The electromagnetic disturbance here necessarily causes light to spread. Now, if that happened only at the point where these two lines cross, you could still get to a point, but it's actually happening earlier. Even as these things are converging, the light is trying to spread back out. So you don't create a point, you create a waste. You create a region where the wave gets packed as tightly as it can, but it's not a single point. The light is still spread out. Now, the size of that spot depends on how slowly these lines converge, but it fundamentally can never be less than the wavelength of the light you're working with. I mean, you can push it, but not very well. What that means is when we use this, no matter what you do with your microscope, there's a limit to how well you can focus light from small regions. And that limits their resolution to, again, be about the wavelength of light, which is is a few hundred nanometers or a few tenths of a micron. So this diffraction process does also affect microscopes. It doesn't affect them quite the same way, but it's one of the limitations that has led people to, build electron microscopes and other things, which have a similar issue, but it's much, much less. Anyway, so that's all for this time, and thank you all for your time and attention.